Right. Let us know Fleming left hand rule to know the direction of force. To know the direction of force on current carrying conductor placed in a magnetic field. Placed in a magnetic field. So, whenever we stretch the left hand, so hold the forefinger, the center finger and the thumb of your left hand at right angles to one each other. Okay, whenever we stretch, whenever we hold our left hand like this, or like this, whatever. So these three are perpendicular to each other. Left hand, forefinger, thumb, middle finger. Forefinger, thumb, and middle finger. So adjust your hand in such a way that the at right angles to each other. So forefinger points the direction of magnetic field. So the forefinger direction of magnetic field. Then center finger points the direction of current. This is current I. Then what about the thumb? Actually, we should place like this. Thumb. Instead of that, we can draw like this. Is force apply. Force of motion, in which direction force applied are equal to U. So B represents magnetic field. Magnetic field means this is forefinger. Forefinger gives the direction of magnetic field. Then the middle finger gives direction of current. Middle finger direction of current. Whereas force by the thumb. To know in which direction the force is exerted on a current carrying conductor placed in a magnetic field by using Fleming's left hand rule. When we adjust the left hand like this, like this, the forefinger denotes the magnetic field. The thumb denotes the force or in which direction the conductor move. Then the middle finger shows the direction of current. In the kick wire experiment also, the direction is downwards. The magnetic field is perpendicular to that. Then in which direction the wire also move, we draw like this one. The diagram also we can draw like this. This is in case if the current direction is upward plane. If it is if the current is moving upward, then you have to take like forefinger as usually magnetic field, then middle finger direction, in which direction it moves towards right side, towards left side. So towards left side further, right side further. Right? This is Fleming left hand rule used to know in which direction the magnetic force or the mechanical force or simply a force acts or exert on a current carrying conductor placed in a magnetic field. Let us now understand how much force is acts on a current carrying conductor placed in a magnetic field. Calculating force. How much force experiences by a charge. Let us discuss with simple electric charge. Then for wire we need to calculate. We have to calculate, right? Calculating force. So calculating the force experience. Calculating the force experienced by a charge placed in a magnetic field. So let us know this is a magnetic field. This is a magnetic field. Big magnetic field. In this direction, V represents the direction or velocity. Of a moving charge. So, if an electric charge moves with velocity v in a uniform magnetic field. This is a uniform magnetic field. In a uniform magnetic field, a charge is moves with velocity v. Then how much force is experienced? A charge q move with velocity v perpendicular to the magnetic field as shown in the figure. The value of magnetic force on the moving charge can be found by using formula F equal to Q V B. So here F means magnetic force, Q magnetic force, F charge is equal to Q, velocity is equal to V. Magnetic field, uniform magnetic field is B. So let's take a charge Q. Q is moving with velocity v perpendicular to the uniform magnetic field. So how much magnetic force is experienced by the charge Q is F equal to QVB. So magnetic force on the charge is the product of three quantities like a charge, speed or velocity, and magnetic flux density. Magnetic flux density. Nothing but magnetic field only. So poles where leave one, the direction of velocity of charged particles V perpendicular to the magnetic field B. Can we generalize the equation for magnetic force on moving? If it has some angle, if the charge has some angle with the magnetic field B, then the force, if it has a theta angle, then force acting here F equal to QVB sin theta. F equal to QVB sin theta. when charges are moves perpendicular to the magnetic field, perpendicular to the magnetic field. If it is the direction of magnetic field, if the charge move perpendicularly, so the charge is move perpendicularly, this much force applied, F equal to Q. If it is parallel to the magnetic field, if the charge is moved parallel to the magnetic field, then what will happen? Theta is equal to 0. Theta is equal to 0. When if the charge is parallel, if the charge is parallel, then theta is equal to 0. Then what will happen? F equal to QVB sin 0 equal to 0. Sin 0. The theta becomes 0. Then what will happen? Sin 0. Sin 0, 0. Then F equal to 0. F equal to 0. So, no force is experienced by a charge when it is moves parallel to the magnetic field. If it is moved perpendicular to the magnetic field, this much force is applied. F equal to QV. If it is moved with some angle, then the force is applied by magnetic field is F equal to QVB sin theta. If the charge is moved parallel at no angle between the magnetic field and the charge. This is the direction of magnetic field. If it is also moves along the direction, no angle, so 0. This is a magnetic field. If the charge moves this direction, perpendicular to each other. If it is make some angle, some force is exerted. So, if a simple electric charge, a small electric charge is moves in a magnetic field, this much force is exerted. F equal to QV. If some angle, F equal to QVB sin theta. Then in case of parallel, completely F equal to 0. F equal to 0. Right. This should be understand. Right hand rule is used when the velocity and the field are perpendicular to each other. This law states that if the forefinger points towards the direction of velocity of a charge of current, middle finger points the field, then the thumb gives direction of the force in which these three fingers are stretched in such a way they are perpendicular to each other. This rule is applicable to positive charge also. So, right hand rule for positive charge. In case of positive charge, right hand rule. This is the right hand rule. So, when we stress the right hand, if the object is charge is moving in a magnetic field, this is direction of force. Thumb direction of force, right? Then B is magnetic field. This forefinger is the direction of charge or direction of current. Right hand rule, not the Fleming left hand rule. So, Fleming left hand rule differs from this right hand rule. Keep in mind this. Right. Then, so here we will discuss for a charge. What will happen or how much force is applied? How much force is applied or how much force is experienced by a current carrying conductor if in case of wire. So, force calculating force experienced by a wire strike. There we can take only a charge, either positive charge or negative charge. Positive charge or negative charge. Let us Let us calculate how much force experiences by a conducting wire. Conducting wire. So the ends of the wire is connected. So here this is the uniform magnetic field. This is uniform magnetic field. In that we place a current carrying conductor. So just imagine that these two ends are connected with a battery. So just like for drawing simple. Like this. So this is the current carrying wire and this is the uniform magnetic field. Uniform magnetic field. Now, how much force is exerted? As just now we discussed, if a charge, a single charge is placed in a or moves in a uniform magnetic field, F equal to QVB, forces are. Forces acts on the body, acts on the electric charge, acts on a electric charge. Let total charge inside the magnetic field. If the total charge inside the magnetic field, this equation for only single electric charge. Now assume that if the total electric charge in the field is Q, the total electric charge is Q, then the force F equal to QVB. QVB. F equal to QVB. Then the time taken by the charge to cross the field. Single electric charge and no problem, but we are taking conducting wire. Conducting wire. So it takes time to move. It takes time to cross the field. To cross the field. To cross the field. Right? Time taken by the charge Q to across the field B, T is equal to L by D. Time taken by the electric charge to cross this field, T is equal to L by B. Here L means length of the wire, B means conducting wire. Okay. Magnetic field. B is the magnetic field, L is the length of the wire. Then L means length, V means V, velocity. How much speed? From this, you can write V is equal to L by T. V is equal to L by T. Substitute this V, this is taken 2, this is taken 1, this is 1, 2, 3. From 3, you can substitute 3 in the equation 1. 3 in 1. 3 in 1, you can write F equal to Q L by T into V. F equal to Q by T. So this should be changed as F equal to QT into LB. QT into LB. Q2 into LB. Right? QT into LB. So magnetic field, force applied, then current. Rule. Okay. This is I, current, direction of current. This is force applied by the magnetic field. Okay. F equal to, you can write here, F equal to Q by T into L B. Q by T into L by. As we know, current means flow of electric charges in a time. So Q by T. So F equal to, this Q by T is nothing but current ILB. F equal to ILB. Since Q by T is equal to I. Since Q by T is equal to current I. So this equation holds well when only when the direction of electric current is perpendicular to the magnetic field. This is the direction of electric current. This is the direction of electric current. So when the current is passed, what will happen? It moves. It moves. So if it is moves, that means okay. So this much of force is applied. How much force is experienced by a current carrying wire when we place in a uniform magnetic field? When we place in a uniform magnetic field is FILB. F equal to ILB. Okay. F equal to IL, this much. The single electric charge at F equal to Q will be, if current carrying wire at F equal to ILB. This is applicable only when the current direction is perpendicular. If it is some angle, we can write F equal to ILB sin theta. Parallel at 0. If it is parallel, it is equal to 0. Okay. This is about in which direction the magnetic force or the mechanical force. The magnetic force or the mechanical force is applied when we place a current carrying conductor in a magnetic field. So here whatever we discussed regarding the straight wire, we know current carrying circular loop or current carrying circular coil also produces magnetic field, right? So if we place the current carrying circular wire in a uniform magnetic field, what will happen? No force is applied because of the magnetic fields are parallel. Circular carrying, how it is produced? Like this. Circular coil, then magnetic field formed like this. So magnetic fields are formed or acts opposite directions with equal force. The same equal force is applied by magnetic fields opposite. One is applied left to right, then other one is applied right to left. So total force acting on the conductor is 0. That's why no force is experienced by a current carrying circular loop placed in a magnetic field, because of the magnetic field formed by current carrying circular loop acts opposite directions with the same force. Similarly, in case of solenoid also, so magnetic field lines are opposite to each other. That's why what will happen? No force is acts. So net force acting because of one the reason. In case of solenoid, when we place a current carrying conductor like this parallel to the solenoid or direction to the magnetic field, parallel to the direction of magnetic field, then see, this is only parallel to the magnetic field. So in case of parallel, we already told that here and here F equal to 0, here also F equal to 0. Here same force is exerted, say force is exerted, but oppositely. Net force acting on the conducting wire is 0. In case of solenoid, current is parallel to the magnetic field line. Magnetic field. Due to these reasons, so force acting on a solenoid which is placed in a magnetic field is 0. Because of this represent the magnetic field of bar magnet. We know like this. So magnetic field formed like this. Both are parallel. Then net force is equal to 0. No force is active. Here equal force is applied opposite direction. No force is equal. Means the force is equal to 0. Here perpendicularly ఉంటుంది. Then some force is applied. F equal to ILB. I means current, L means length of the conductor, B means magnetic field or magnetic flux density. F equal to case of small electric charge, F equal to force, Q means charge of charge, Q means velocity or speed, B means magnetic flux density. So this is about how much force is experiences by a conductor when we place in a magnetic field. So that's all for today's session. Thank you so much for watching. Then once again, I am requesting you, if you did not subscribe, please subscribe the channel. Did not share the channel with your friends, please share the channel. Like the video, make a comment for developing for your encouragement. So watch the videos accordingly, the topics which are explaining by your teachers in your school. Thank you so much. Sign off. Bye.